All right. Today we're going to implement a multi-threaded pool allocator in C. Now, before we start with the actual implementation, I want to go through a couple of topics. I want to kind of talk about memory allocation in general. What is an allocator? What is a pool allocator specifically? And what do I mean by multi-threaded allocation? I also want to talk a bit about the motivation behind this video, why this topic specifically, and why record it. I hope that this can help you make a decision if this is actually worth your time. Then I want to define kind of the API of our allocator. And finally, I want to make a quick plan of how we're going to implement it. So let's talk a bit about allocation. If you've used C before, you've probably used malloc, which is the C standard library general purpose allocator. And malloc is general purpose in the sense that you can use it for allocations of just a couple of bytes up to allocations of multiple gigabytes. And you can also use it from multiple threads without handling the synchronization on the call side. The synchronization is handled for you inside of malloc. What we are trying to build today, the pool allocator, is not general purpose. It's meant to allocate objects of one size and one size only. Now, the benefit of making something not general purpose is that you can often make optimizations for that one specific case that you are handling. And that's what we're kind of trying to do. When your allocator only handles objects of one size, it makes it a bit easier to kind of keep track of what locations in memory are still available to be allocated. And the way we're going to do it specifically is we're just going to have one region, one contiguous region of backing memory, and we're going to subdivide it into sub-allocations of the size of the object that we are allocating. And then we're just going to hand out indices into this backing memory. So in the normal case, we don't need to do any extra allocations when the user calls alloc. We're going to do one allocation in the beginning, one call to malloc, and that's basically it. Now, once we are a bit further along with this project, I do want to handle the case that we've run out of backing memory and we actually need to allocate more memory to be able to hand out more objects to the caller. But I think in the first pass, I just want to allocate the backing memory once. And once we've run out of backing memory, I'm just going to return null from our allocate function. Now about the multi-threading. I think there are a couple of interesting subtopics within that. In the first pass, we're going to use a simple mutex log. Basically, we're going to call mutex log at the beginning of our allocate and deallocate functions, unlock at the end, and just like that, we've protected our internal allocator state. That's not optimal, probably. I'm actually not sure. This is kind of the reason why I want to explore this. I would like to compare using a mutex to protect the internal state and using atomics and kind of a bit an alternative way to keep track of free allocation slots using atomics. I think it's going to be quite interesting. And I wanted to compare the performance between using a mutex and using atomics. I've heard in the past that using a mutex to protect shared state is actually not that slow. It's only slow in many cases if you have contention and threads have to actually wait until they can execute the state between mutex lock and unlock. But the actual locking shouldn't be expensive. And I kind of want to verify that claim, understand it a bit better. So I think that's kind of it for the theory. I think next up we can go ahead and define the API for our allocator. So we're going to need some way to initialize our allocator. So we're going to have a function that's something like pool init. It's going to take a pointer to our allocator. We obviously need an alloc function. And I think actually in the beginning, I want to make it a bit more specialized. I don't want to kind of return objects of an arbitrary size that would be set during the initialization. I want to make a specialist allocator for one specific type. So I'm just going to invent that type right now. I'm going to call it struct entity. It's going to have some attribute. And we can also just create a struct for our pool. It's going to have nothing in the beginning, but we're going to fill that later. And our alloc function is no longer going to return void star. It's going to return a pointer to an entity. It's going to be pool alloc. It's also going to take pointer to our pool. And I think it actually doesn't need to accept anything else but the pool. Because we don't need to pass it a size. The size is constant. It's the size of struct entity. Once you make it actually kind of generic and able to handle objects of different sizes, the init function is actually going to take probably like a size t object size, and yeah, that might be the way we handle it in the future. But for now, we can only allocate struct entities, and that's it. So on the opposite side, we will need a pool dalloc as well. That function is not going to return anything. Pool dalloc is also going to accept pool. Oh, and it also needs to accept the pointer to the object that's going to be deallocated. And that's basically it for now. APIs for allocators are pretty simple, and in this case, even more simple because we are not generic. So I think the way I want to go about the implementation of these functions, I want to start very simple. I think I'm just going to have a static array of entities. Let's say, actually, we can make this a constant. Object count, let's make it 16. That's going to be the length of our array. And now we need some way to keep track of what slots in our backing memory are still available for allocation. And I think kind of the simplest way to do that is to just have a stack of indices into the entities array. And with each allocation, we would just take the topmost element of our index stack and return a pointer to the entity at the index that that stack object or stack item is pointing to. Maybe it actually makes sense to kind of illustrate what I'm trying to do here. So we have entities. Let's just have 4 entities. And we're also going to have, as I mentioned, the stack of indices into that backing memory. Actually, maybe it does make more sense to do it horizontally. 2 and 3. And when you call alloc, we would remove one item of the stack. So now there's nothing here. And these 2 rows are kind of 2 separate arrays. So we would have like a second array in here, and that's just free. Yeah, just call it free object count. Actually, maybe just free indices. And the number of indices has to be the same as the number of entities, because each index corresponds exactly to one slot in our backing memory array. And also we need a pointer to the top of the free indices stack. Free top. So at the beginning, when we initialize our allocator, free top would point to, or would be set to the value 3, meaning the topmost item on our stack is the fourth index on our free indices stack, the item at index 3. And then when we allocate an object with our allocator, we would change the stack pointer to now point to the third element on our free indices stack. Basically, we remove one item of the stack, and we would return a pointer, in this case, to E4, entity 4. So basically, to get the address of E4, we would do entities free indices at free top. This is kind of the pointer. This is the pointer to the entity that we're going to return. And then obviously it's important that we decrement our stack pointer so it points to the next lowest item on the stack, so that the next time someone calls alloc, the index is going to be 2, and we're going to point to E3. And that's going to be the pointer that we are going to return. That's kind of the rough plan. I think we can actually start implementing these functions, but first let me just make sure that the compilation is working fine. I'm just going to print something here. I'm going to include stdio so we can print. And hope that this compiles. We actually need a simple build script. So let's just write a build sh. I'm going to compile main.c into a main executable. And then in the same script, we can also just execute the binary. Let's go back here and let's just run our build script. Okay, we're seeing test, everything compiles fine. And I think we can start implementing these functions. So pool init, what do we need to do? We actually don't need to initialize our entities at all. The way our allocation API is going to work, kind of similar to malloc, we're just going to give you the memory location. We're not going to initialize it for you in the same way that malloc doesn't zero the memory before it gets returned to you. But we do need to initialize our free indices. I removed the illustrations I had before, but if you remember, the stack was initialized to 0, 1, 2, 3. And we kind of need to do the same thing now for our free indices stack. So we're just going to write a simple for loop that goes through all the indices. And for each one, it will free indices at I. We will just set it to I. Index 0 is going to be 0. Index 1 is going to be 1. And we're going to set our stack pointer to object count -1. So the last element of this array. Okay, that's kind of it for this. Actually, let's make this function static. Like for now, we're just going to call these functions from this file, so they don't need to be visible to the outside world. Now, our alloc function, as I said, needs to look at the topmost item on the free indices stack. It needs to return a pointer to the item at that index. And then it's going to decrement the stack pointer by 1. But the first thing that we need to do is we need to check if we actually have objects left to be allocated. Like if we have enough backing memory to fulfill that request. And the way we're going to know if we do have enough space is checking if free top, the top of our stack, is at 0 or greater. Yeah, that should be right. So, because 0 is still a valid item, like it's the first item on the stack, so that's still valid. But if it's -1, then we obviously can't dereference the item at -1. So if pool free top is less than 0, we're just going to return null. But otherwise, we first get the index. Indices at pool free top. We're going to decrement this value. And then we can use the index to return a pointer to the entity at that index. random pointer. And I think that should be fine. Yep. I was just thinking about the case when object count is 0. But actually, I think that even in that case, this logic still works because object count here is going to be 0, which means free top is going to be -1. And that means that on the first allocation, this one is going to return null. So I think that's fine. Now, our dalloc function. Since we get a pointer, we first need to go back from that pointer to an index, which means we um how are we going to do that? Let's convert this to a character pointer first. Um, entity minus actually, I think I shouldn't do this as pointer. I should just use pointer diff subtract the base location and divide that by the size of entity. Yes. Divide that by the size of each entity. And I think for this to work, I actually need to include std_def. Pool init needs the name. Yes. Okay, cool. That works. Yes, pointer diff pool entities. That's going to give us the offset. Divide the offset by the size. Yeah, that should be fine. And we need to put that index back on the stack of free indices. So what we're going to do, we have pool free indices. At the index, pool free top. Actually, no, we need to increment it first. Yes, we need to increment it first. If you just think about the case where we've taken all the free indices of the stack, free top is going to be at -1. So we first need to increment it by 1 and then write to the element at what is now index 0 of the stack. For indices, and that's going to be the index that we just calculated. Free top set free indices to our index, yeah? I think that should be fine. Let's just try creating a pool. See if that works. Let's just try to allocate all the objects. Pool alloc Cool. And let's assert that if we try to allocate one more object, that we're going to get back null from our allocator. Undeclared function, yes, we need to include assert.h. And that works. Cool. So I think at this point, I kind of want to test that the basic logic of our allocator works. And what I want to do specifically is I want to return objects to our allocator in a different order than we allocated. Meaning if we allocated 3 to 1, 0, I want to deallocate it, for example, again in 3 to 1, 0, which means our indices are now going to be kind of in reverse order after we've deallocated the objects again. Just to test if this logic works on a basic level. And also to see if our dealloc function works. So I'm just gonna create entities, just an array of entity pointers. And we're gonna need object count as the length of that array. And we're just gonna set the result of our alloc function as the value of those entity pointers. Entities at index I is equal to that. Which means if our free indices array is initialized to 0, 1, 2, 3, our entity pointers are going to be a pointer to the third, a pointer to the second, pointer to the first, or index 1, rather, and then pointer to index 0. That's going to be the contents of our entities array down here. And if we just return them by just looping through that array, we should, in theory, just get what I wanted. Which means we're just going to do a pool dealloc. And we're going to give it the entity pointer at index I. And what we're now trying to have is that our free indices array should now be 3, 2, 1, 0. So let's try to assert for that. Free indices at index I should be object count minus I minus 1. Struct pool is not a pointer. Yes, that is true. Assertion failed. Oh, that totally makes sense because we've now deallocated our objects again, which means we have objects to allocate again. And that seems to be fine. Cool. Maybe it makes sense to kind of put this logic into its own function, just so we have like some way to test if our allocator works along the way. Pull init. Yeah, let's just do the entire thing. I mean, maybe it's a bit early to pack that out into its own function, but that should be fine. This can go in here to have a bit of an explanation of what this is. Yep. All right. And that's basically it. We have a very basic pool allocator that at the moment only works from one thread. And in fact, we can just demonstrate that it doesn't work from multiple threads and at the same time kind of have a bit of an intro to thread sanitizer. So I'm just going to go in our build script and I'm going to add a flag to our compile flags that enables thread sanitizer. Sanitize thread. Go back into a C file and let's try if this still builds. It does. Actually, I'm going to rename this function into pool test single threaded. And we're going to create a different function. For now, I'm just going to do it in line to test if this works from multiple threads. So what we're going to do for that is we're just going to create a couple of threads. And I'm going to define thread count 4 for now. Put those threads here. Thread count. And I'm just going to create those threads. P thread create. Actually, is it create or is it init? Man, P thread create. Yeah, it's create. Cool. It takes a pointer to the thread. It takes a pointer to the attributes. For now, we don't really need special behavior for our threads, so I'm just going to set the attributes to null. It takes a start routine and it takes an arguments pointer. So the way the pthreads API works is a thread needs some piece of code that it's going to execute when the thread starts. And you tell pthreads what function that should be by just giving it a function pointer. I can actually just show you what that looks like. Just going to create a static function that returns a void pointer. This is kind of interesting. Pthreads also has a way to return a value from a thread. So there's, if we go back to the man page, there's a function called pthread join. And this function kind of tells the caller to wait until the thread that you give it as an argument has terminated. And then you get the pointer that it returns from its execution function written to a value pointer, the second argument to this function, right here. that value is going to be set to the result of the function that the thread executes. So you kind of have a way to communicate values out of the function that the thread executes. Now, you don't really need it because when you create the thread, you also give it this arguments pointer. Actually, I think it's easier if we just implement it instead of me just talking about it. Let's just write thread function. It takes an arguments pointer. This is the pointer I just mentioned. And for now, we're just going to return null. So in pthread create, we first of all give it a pointer to the thread we are trying to create. We give it a pointer to the thread attributes, but for now we're just going to set that to null. This is going to give us just default behavior. It now wants the function pointer, which is just thread func. And this next value is going to be the value that is passed to the thread execution function. So this args pointer is going to be whatever value we set right here. So for now, we're just going to set it to null. And in here, we're going to just print that value. Now I'm just going to execute it like this, and we're going to see that this will not work. For multiple reasons, apparently. More conversions than arguments, that is absolutely correct. We need to actually put our args pointer here. Oh yeah, we don't include pthread.h. And now we get our first thread sanitizer warnings. The first warning is that we've leaked threads. And what that means is that we've created these pthreads here, but we never do anything with them. And what thread sanitizer wants us to do is to create another loop right here. And here we should wait until the thread has executed. Basically, it noticed. This is actually what I wanted to show, but we get a warning before I can even show that. Or actually, the warning shows us that this is wrong. Printing in here isn't really going to do anything because we create the threads and then we just exit from our function and with that from our process, which means this thread function never has time to even execute. Or if it does, then it's kind of random. It's by chance that it gets enough time to execute. So what we actually need to do is we need to wait until the thread func has returned. And we do that by calling pthread join and giving it the thread that we want to wait on. Yeah, if I remember correctly, this needs a second argument that's pthread join, yeah, the value pointer. For now, we're just going to set that to null. And now thread sanitizer should be a bit happier with us since we're now waiting on all of these 4 threads. And now we should also see that those args pointers should actually be printed. And looks good. Now, I wanted to actually show how it goes wrong. So actually, let's try to do that. I'm going to comment that out, and I'm going to go to our build script and actually just not use thread sanitizer for now. And now we should see that we kind of get a non-deterministic behavior. Sometimes we see one address in the first time, we saw two addresses. Basically, it's non-deterministic what threads make it to this line of code and actually get to execute this print statement. But when we uncomment this again and actually wait for the execution to end, then we're fine. So now let's re-enable thread sanitizer. Okay. So instead of just printing the arguments pointer, let's actually try to do something useful with the pointer. And what I want to do is I want to create a pool allocator again. Pool init, give it a pointer to the pool. And we're going to have all of these 4 threads try to access the pool allocator at once without any synchronization. Just going to give it a pointer to the pool. And in here, we're going to cast our arguments pointer to a pool pointer. But now let's just print it. Yep, looks fine. We finished our pool, and let's try and see what happens when we just call alloc. Pool alloc and give it our pool. And we see that rightfully, thread sanitizer complains. Because what are we doing here? Each thread is going to call pool alloc. And this is fine. They're just, like, the first line is fine. They're all reading from free top. Multiple threads can read from the same value. That's not an issue. But where we do have an issue is right here. All the threads are trying to read and then decrement free top. Now, written like this, it looks like this is one operation. Like, the thread reads the value, decrements it, it's all one thing. But that's obviously it's not the case. Not obviously, it's not the case. Which means that in theory, we can get the following behavior. We can have thread one read free top and get the value 3, for example. And we could have thread 2 read free top and also get the value 3. And then thread 1 might decrement the value, which means it sets like write free top and set it to 3 minus 1, so 2. And because thread 2 also read the value 3, it will do the exact same thing. 3 minus 1 is still 2. So now this is a data race. 2 threads have read and set the value of free top to the exact same thing. What we actually wanted is for the read and the decrement operation to kind of be one thing, to be atomic. Basically, what we want to have is read and decrement. It's going to read 3 and it's going to set it to 2. And then thread 2 is going to read and decrement as well. And it's going to read 2 and set it to 1. But at the moment, we don't have any kind of infrastructure to actually get this behavior. By default, the minus minus operator isn't atomic. And this is basically exactly what thread sanitizer is trying to tell us. If we run this again, it complains about a read of size 4. Actually, to be able to interpret this better, I think it actually makes sense to print out the pointer to our free top variable. Before we do anything. So I'm just going to print free top. Free top. So we can see that thread sanitizer actually complains about that variable. Oh. It's not a pointer. Oh, yes. Bool dot. Actually, where's my print? Yeah, okay. So our pointer has EB 250 at the end. And we can see that indeed thread sanitizer complains about a read of size 4 at the pointer to our free top. After there's been a write of size 4 to the same variable on a different thread without any kind of synchronization. And this is exactly what we expect. So now let's try to not have this happen. So how do we enforce this synchronization? Now, in the beginning, I mentioned that there are at least 2 ways to accomplish our goal here. The simplest way, and the way that we're going to implement first, is to use a mutex to protect our shared state, to protect the state that can be accessed on multiple threads. In this case, the free top variable. A different way is to use atomics. And we're also going to do that, but not right now. And that's kind of a very interesting topic to explore later. But for now, let's just use a mutex for this. pthread also comes with a mutex type, pthread mutex. And we're just going to put it inside our pool struct. And in the pool init function, we're just going to initialize the mutex. So I think for pthread mutex, the function is actually called mutex init. Yeah. It takes a pointer to the mutex and to attributes. Right now, we're just going to set the attributes to null. Pool mutex and attributes are null. And now what we need to do here is we're going to call pthread mutex log. Going to give it a pointer to our mutex. And now we have a bit of a problem because we return from this function in 2 different spots. So if we call pthread mutex unlock this is just extremely wrong because we've already returned on all possible paths. So this is never going to get called. And we need to do a couple of changes here. I think what I'm going to do is I'm going to basically create a local variable entity. This is our result pointer. It's going to be initialized to null. And I'm going to reverse this if statement to only execute the following two lines. If our top of the stack is 0 or greater. So now we can call pthread mutex unlock without any problems here. And then just return our result. So just to verify that this still works, if we have a negative stack pointer, if free top is -1, we don't execute this. We're still going to lock and unlock our mutex. That's what we want to do. And then we just return null. So this should be fine. We also need to do the same protections for our dalloc function. Because here as well, we access the free top variable in a way that isn't synchronized. Multiple threads can read and change this variable at the same time. But here I think it's actually a bit easier to circumvent that. We're going to call lock on the mutex. And down here, we're going to call mutex unlock. We don't return anything, so this is a bit easier. Okay, I think this is actually fine. And let's try to run this. So we're going to allocate, and if we've done things correctly, we should now no longer get thread sanitizer warnings. Okay, we seem to be deadlocked, which means I've probably called pthread mutex lock. Oh, yes, that totally makes sense. I'm still returning from here. What we actually need to do is set the result variable to our pointer. And let's run it again. This looks much better. Let's actually remove this print statement. Yeah, that looks good. So as a next step, what I want to do is I want to make our pool allocator a bit more generic. Right now, we always return entity structs. But what I would actually like to do is I would like to turn this into just a void pointer, a generic pointer to some backing memory. And I would like to give the pool init function an object size and an object count. So then the caller can decide what count and size to call the allocator with, and we can just accommodate that request. But I think before we do that, I want to take a quick break and see you then.